Hello my friends, I'd want to welcome you back to my channel. Today we are going through another further pure maths paper. This is 9231/11 for the May-June 2021 sitting. So we are going to jump right in and we are going to start with question number 1. So in question number 1 we've got mathematical induction. So they say, prove by mathematical induction that 2 to the power of 4n plus 31 to the n minus 2 is divisible by 15 for all positive integers n. Okay, so we have here 2 to the power of 4n plus 31 to the power of n minus 2. So here we're going to start by proving for n is equal to 1. Now if n is equal to 1, it means we're going to be having 2 to the power of 4 of 1 plus 31 to the power of 1 minus 2. If we're going to simplify this, we're going to get 2 to the power of 4 times 1, that's 16, and that's plus 31 minus 2. Now this will give us 45, and we know that 45 is divisible by 15. So we can hence conclude that this is true for n is equal to 1. So that's the first part. So now we're going to make the assumption. So assume true for n is equal to k, which means that the formula 2 to the power of 4k plus 31 to the power of k minus 2 should be divisible by 15. In other words, it's a multiple of 15. So we can just say it's equal to 15a, or you can use any other letter, but 15a means a multiple of 15. So here, that's the assumption that we're going to make. So now we can prove for n is equal to k plus 1. So we want to see if this formula is going to be true for n is equal to k plus 1. So that should mean we'll be having 2 to the power of 4 of, in place of n, we're going to put k plus 1, and that's plus 31 to the power of k plus 1 minus 2. So this is 2 to the power of 4k plus 4, and that's plus 31 to the power of k plus 1 minus 2. So this is 2 to the power of 4k times 2 to the power of 4 plus 31 to the power of k times 31 to the power of 1, and that's minus 2. I'm just trying to simplify this. So we have 16 of 2 to the power of 4k, and that's plus 31 of 31 to the power of k minus 2. So from the assumption, we can say that 2 to the power of 4k is equal to, if we make 2 to the power of 4k subject, we'll be having it coming out as 15a minus 31 to the power of k plus 2, which means that for what we have here, continuing with our working, it will be 16, but in place of 2 to the power of 4k, we put in this thing from the assumption. So we put in 15a minus 31 to the k plus 2, and that's plus 31.31 to the power k minus 2. Now 16 times 15 is 240, so we have 240a here, and it's minus 16 of 31 to the power k. 16 times 2 is 32, and that's plus 31.31 to the power k, and that's minus 2. And simplifying this a little bit more, we will be having 240a, then minus 16 of 31 to the k plus 31 of 31 to the k will give us 15 of 31 to the power k, and 32 minus 2, we will get 30. Now what we have right here is actually divisible by 15. So if we factor out 15, we'll be having 16a plus 31 to the power of k plus 2. So this thing is exactly divisible by 15. So we say this is divisible by 15. Hence, by mathematical induction, it is true for every positive integer value n. And we have thus proved by mathematical induction. So that's how we can work out this question here, which is question number 1. Let's scroll down to question number 2. Question number 2. Part A. Use standard results from the list of formulae MF19 to find the summation from r is equal to 1 up to n of the form 1 minus r squared in terms of n, simplifying your answer. So we will need the list of formulas here, and these are the standard results that we are expected to use. So we are saying for the summation from r is equal to 1 up to n of the form 1 minus r squared, this is going to be equal to the summation from r is equal to 1 up to n of 1 minus the summation from r is equal to 1 up to n of the form r, and that's minus the summation from r is equal to 1 up to n of the form r squared. So the summation here is kind of distributive. So for the first part, we are going to get n. And for the second part, we are going to use this standard result. So we'll be having half n of n plus 1. Then for the third one, we're going to use this standard result. And we are going to be having a sixth of n plus 1 of 2n plus 1. So we can simplify this. So we'll be having n minus, and here we'll be having half n squared minus half n. And that's minus, and here we can simplify the two brackets, n plus 1 and 2n plus 1, to get 2n squared plus 3n plus 1. So we can continue simplifying. That's n minus half n squared minus half n, and that's minus, if we multiply, minus a sixth n times 2n squared, we get a third of n cubed, and minus a sixth n times 3n, we get minus a half of n squared, and that's minus a sixth of n. Now we can carry this forward. So n minus half n minus a sixth n, this is going to give us a third of n. And we also have minus half n squared minus half n squared, and we get minus n squared for that. Then we also have the term in n cubed, so that's minus a third n cubed. So this here becomes the final answer for part A. So let's scroll down to part B. On part B, they say, show that the fraction 1 minus r squared over r squared plus 2r plus 2 bracket r squared plus 1 is equal to r plus 1 over r plus 1 squared plus 1 minus r over r squared plus 1. And then they say, hence use the method of differences to find this summation thing here. Alright, so let's start with the first part of this question. Now, we want to show that these two fractions are equal, and I'm gonna make use of the right hand side to prove that it is going to give us the left hand side. So for that, for this fraction, I'm going to find the common denominator, which is the product of these two brackets. So this is r plus 1 squared plus 1, which I can expand to r squared plus 2r plus 2, bracket r squared plus 1. So here I'll multiply this 2 to get r squared plus 1, multiplying r plus 1. And again multiply this 2 to get r of this, which is r squared plus 2r plus 2. Okay, so let's simplify this. So this is going to give us, the numerator will give us, if we expand these two brackets, we get r cubed plus r squared plus 1. And then that's minus, expanding these brackets, we get r cubed minus 2r squared minus 2r. So this is all over this denominator. So we can continue simplifying. So grouping like terms here, we've got terms in r cubed. So that's r cubed minus r cubed. So that's going to give us 0. Then we have the term 1. And the terms in r, we've got r minus 2r, which is minus r. Then the terms in r squared, we've got r squared minus 2r squared, which is minus r squared. And it's all over the denominator. So with what we have thus proved that this equation is true. So we say here this is equal to the left hand side, hence shown. So let's go on to the next part of the question. So they say here, hence use the method of differences to find the summation from r is equal to 1 up to n of the form 1 minus r squared all over r squared plus 2r plus 1 bracket r squared plus 1. Alright, so I'm going to take this summation. This is the one we want. I'm going to paste it here. So we can use the identity that we got, because from the initial part of the question, this expression here is equal to this expression here at the top. So let me take it as well and place it here. So these two expressions are equal. So we're going to make use of this for the method of differences. Okay, so for the method of differences, we are going to say for r being equal to 1, here if we substitute 1, we are going to get 1 plus 1, which is 2, over substituting 1 for the denominator. That's 1 plus 1, that's 2, 2 squared, that's 4, 4 plus 1, that gives us 5. And then that's minus, substituting 1, we get 1 over 1 squared plus 1, which is 2. Then for r being equal to 2, we are going to get here 2 plus 1, which is 3. And then here we get 2 plus 1, that's 3, 3 squared, 9, 9 plus 1, 10. Minus, substituting 2 here, we get 2 over 4, 2 squared plus 1, which is 5. Then for r being equal to 3, we are going to get 3 plus 1, that's 4. And that's 4 over 3 plus 1, that's 4, 4 squared, 16, 16 plus 1, 17. Then that's minus, and here we're going to get 3 over 3 squared plus 1, which is 10. So we continue going, and then we reach the term r is equal to n minus 1. And for that term, if we substitute n minus 1 for r at the top here, we get n minus 1 plus 1, which is n over, and then at the bottom, n minus 1 plus 1, that's n, so we get n squared plus 1, and then that's minus, and here we get n minus 1 over, and that's going to be n minus 1 squared plus 1. So that's what we're going to get here. Then when r is equal to n, what do we get? We are going to get n plus 1 over n plus 1 squared plus 1, and that's minus, and we get n over n squared plus 1. So I think you can see that if we're going to add these terms, we are going to have some of them eliminate, like this 2/5, s to minus 2/5 to get 0, 3 over 10 and minus 3 over 10, which means 4 over 17, we have another number to add to and eliminate, and so will this term. And even you can see if we add this term and this term, they're also going to add and eliminate. So eventually we are going to be left with minus a half and n plus 1 over n plus 1 squared plus 1. So we are saying here, this summation therefore is equal to minus a half, and then that's plus n plus 1 over n plus 1 squared plus 1. And this is the answer. Let's go on to part C. So on part C, they say, deduce the value of the summation from r is equal to 1 up to infinity of the form 1 minus r squared over r squared plus 2r plus 2 bracket r squared plus 1. So you need to understand that this here is the same as the limit as n approaches infinity of minus a half plus n plus 1 over n plus 1 squared plus 1. So this is what we have. So for this one here, you can notice that we have got minus half, and the limit will simply just be minus a half. And then if you look at this fraction here, you can see that as n approaches infinity, the denominator will increase at a much faster rate than the numerator as n approaches infinity, since we have n plus 1 squared plus 1 here, and at the top we only have n plus 1. So this whole fraction here tends towards 0 as n approaches infinity. So the limit here will simply come out as minus a half. And that's the answer there to part C. Question 3. The equation x to the power 4 minus 2x cubed minus 1 equal to 0 has roots alpha, beta, gamma, and delta. So on A, find a quadratic equation whose roots are alpha cubed, beta cubed, gamma cubed, delta cubed, and state the value of alpha cubed plus beta cubed plus gamma cubed plus delta cubed. So we have right here a quadratic equation. And in order for us to find the quadratic equation with the roots alpha cubed, beta cubed, gamma cubed, and delta cubed, we're going to say let y be equal to x cubed. So when we do that, we make x the subject, so it means x is equal to y to the power of a third. So in this quadratic equation, which is in terms of x, we're going to substitute y to the power of a third in place of x to get a new equation with these roots. So this means we'll be having in place of x on x power 4, it becomes y to the power of a third to the power of 4. And that's minus 2 of y to the power of a third to the power of 3 minus 1 equal to 0. So we can simplify. We'll now be having y to the power of 4 over 3 minus 2 of, here if we multiply a third times 3, we get 1. So we'll now be just having 2y, and that's minus 1 equal to 0. So it means we can make y to the power of 4 over 3 subject, which is y to the power of 4 over 3 is equal to 2y plus 1. Now we can raise both sides, or we can cube both sides, or raise to the power 3. So it means we'll now be having on the left side y to the power of 4, and on the right side, if we raise 2y plus 1 to the power 3, we'll now be having 2y cubed plus 3 of 2y squared plus 3 of 2y plus 1. So we can simplify that, and that's going to give us 8y cubed plus 3 times 4, that's 12y squared plus 6y plus 1. So if we take everything to one side, that is to the left side, we'll eventually have y to the power of 4 minus 8y to the power of 3 minus 12y squared minus 6y minus 1 equal to 0. So what we now have here is the quadratic equation with the roots alpha cubed, beta cubed, gamma cubed, and delta cubed. Now also according to the question, they say state the value of the sum of the roots alpha cubed plus beta cubed plus gamma cubed plus delta cubed, that is for the new quadratic equation, which is in terms of y. So to get the sum of roots, we know that for a quadratic equation, the sum of roots is obtained by minus b over a. So we're saying here alpha cubed plus beta cubed plus gamma cubed plus delta cubed is equal to minus b. B in this case is the coefficient of y cubed, which is minus 8. So it's minus of minus 8 over a. A in this case is the coefficient of y to the power of 4, which is 1. So we are going to get the answer as 8. So that's the answer right there. So we're done with part A. We can now scroll down to part B. On part B, they say, find the value of 1 over alpha cubed plus 1 over beta cubed plus 1 over gamma cubed plus 1 over delta cubed. Okay, so in order to get the value of this, what we're going to do is we are going to express this as a single fraction. So we will have a common denominator in alpha cubed, beta cubed, gamma cubed, and delta cubed. So that's a common denominator right there. And at the top, we'll be having, if we divide alpha cubed into the denominator, we'll be left with beta cubed, gamma cubed, alpha cubed. And that's plus, dividing beta cubed into the denominator, we get alpha cubed, gamma cubed, and delta cubed. And dividing gamma cubed into the denominator, we have alpha cubed, beta cubed, and delta cubed. And dividing delta cubed into the denominator, we get alpha cubed, beta cubed, and gamma cubed. So for this, we are going to be using the quadratic equation that we got in part A. So for the numerator, you can see that the numerator is the sum of the product of triples. And for a quadratic equation, the sum of the product of triples is obtained by minus d over a. In our case, d is the coefficient of y, which happens to be -6. So we just have this for the sum of the product of triples. And at the bottom, we have the product of roots. And we know that the product of roots for a quadratic equation is e over a. In our case, e is the term -1. And that's -1 over 1, which is just -1. So it's like we've got 6 over -1, which is -6. So the answer here is -6. We can scroll down to part C. So on part C, they say, find the value of alpha to the power 4 plus beta to the power 4 plus gamma to the power 4 plus delta to the power of 4. Now for this equation, we are going to use the first equation in terms of x. So we are going to take this equation here, and that's the one we're going to use for part C. So I'll just put it here. So for this equation, we can make x to the power 4 subject. So it's x to the power 4 is equal to 2x cubed plus 1. Now, since alpha is a root of this equation, we can say alpha to the power 4 is equal to 2 alpha cubed plus 1. And also, since beta is a root to this equation, we can safely say beta to the power 4 is equal to 2 beta cubed plus 1. Gamma is also a root, so gamma to the power 4 is equal to 2 gamma cubed plus 1. And delta is a root, so delta to the power 4 is equal to 2 delta cubed plus 1. Now, if we add these four equations, on the left side, we'll now be having alpha to the power 4 plus beta to the power 4 plus gamma to the power 4 plus delta to the power 4, which is, if we add the right side, we get 2 of alpha cubed plus beta cubed plus gamma cubed plus delta cubed. And that's plus 1 plus 1 plus 1 plus 1, that's 4. Okay, so for the sum, here we get 2 off, and here we've got the sum alpha cube plus beta cube plus gamma cube plus delta cube, which we got a little bit earlier as 8 right here. So that's 8. So we have 8 here, and that's plus 4, which is 16 plus 4, which gives us 20. So the answer to part C is 20. And that's it for this question. We can now scroll down to question number 4. Question number 4. The matrix M represents the sequence of two transformations in the xy plane given by a rotation of 60 degrees anticlockwise about the origin, followed by a one-way stretch in the x direction, scale factor d, where d is not equal to 0. So on A, find M in terms of d. So here we've got a composite transformation, and first we have a rotation of 60 degrees anticlockwise about the origin. Now here, I would want you to consider a unit square on the Cartesian plane. And for this unit square, if we are going to rotate it by 60 degrees about the origin going anticlockwise, we will eventually have the transformed square being this one. Now, the point 1, 0 has its image as this point, which has an x-coordinate of half and the y coordinate of root 3 over 2. This you can find using simple trigonometry. That's the unit cosine of 60 and the unit sine of 60. So we're saying here the point 10 is being transformed onto the point a half and root 3 over 2. And what about the point 01? The point 01 here has been transformed onto this point here through the rotation of 60 degrees going anticlockwise about the origin. So the new coordinates are minus root 3 over 2 and a half. So we're saying the point 01 is being transformed to minus root 3 over 2 and a half. So from combining these, we can come out with the operator matrix. So let's write it down here. So we're saying the first transformation, that is the rotation of 60 degrees anticlockwise about the origin. The matrix is a half and root 3 over 2, then minus root 3 over 2 and a half. So this is the matrix. Now let us consider the one-way stretch in the x direction. So in this case, the unit square is being stretched parallel to the x-axis and the scale factor is d. So that automatically means that the point 10 has been transformed onto the point d0. And the point 01 remains invariant since it's a one-way stretch. So the point 01 is mapped onto itself. So by combining these, we come out with the operator matrix. So I'll write that down. That's the one-way stretch with factor D. The matrix is D0, 0, 1. So we now have the two matrices. Now, in order for us to come with the matrix M, which combines the two matrices, we will multiply the two matrices representing the transformation in reverse order. So since the first transformation is the rotation and the second transformation is the one-way stretch, we will pre-multiply with the one-way stretch matrix. And here we'll be having a half and root 3 over 2, then minus root 3 over 2 and a half here. So I'll multiply the two matrices. So row by column, d times a half plus 0 times root 3 over 2, that gives me half of d. Then d times minus root 3 over 2 plus 0 times a half, we get minus root 3 over 2d. Then 0 times a half plus 1 times root 3 over 2, we get root 3 over 2. And 0 times minus root 3 over 2 plus 1 times a half, we get a half. So this becomes the matrix M. So we're done with part A. We can now move on to part B. So on part B, the unit square in the xy plane is transformed by M onto a parallelogram of area half d squared units. Show that d is equal to 2. Alright, so right here we obtained the matrix for transformation M, which I'm going to take from here. So here it is, and I'm going to find the determinant of this matrix. So that's going to be half d times a half. So that's half d times a half, and that's minus the product of minus root 3 over 2d and root 3 over 2. So this is going to give me here a quarter d, and that's minus of minus 3/4. That's 3/4 d. So that's 1/4 d minus 3/4 d, which is just 1/4 d plus 3/4 d, which gives us d. Now therefore, if I multiply the determinant of m, which happens to be d, times the area of the unit square, which is 1, they say here that this transforms to a parallelogram of area half d squared. So I can solve for d here by multiplying both sides by 2, so that's 2d is equal to d squared, and dividing both sides by d, I get d coming out as 2. Actually, d has 2 values, of which the other one is 0, but d cannot take the value 0. So here I'll eventually get the value of d coming out as 2. And that's the answer to part B. Let's scroll down to part C. So on part C, it says the matrix N is such that Mn is equal to the matrix 1, 1, a half, and a half. So on C, they say find N. Now, in order for us to find N, we will need to first find the inverse of M. Now, on part A, we had obtained the value of M as this one. And on part B, we discovered that the value of D is 2. So if we substitute 2 for D, we will get M coming out as this. Now, the inverse of M, therefore, so M inverse should therefore come out as 1 over the determinant of M, which is 2. And here, switching the positions of 1 and of a half, we'll be having a half here and 1 here. And for this 2, if we are going to change the signs, then we will have this becoming root 3 and this becoming minus root 3 over 2. So we now have M inverse. Now we know that to get rid of the M on the left hand side so that we're left with N, we have to multiply both sides by the inverse of M. So if we multiply the left side by the inverse of M, then we'll be left with N on the left side. And we're going to multiply the right side again with the inverse of M. So that'll be a half here. That's M. Multiplying the matrix 1, 1, a half, a half. So let's do the multiplication. So here, I'll carry down the half. Then I'll multiply a half times 1 plus root 3 times a half. I get a half plus root 3 over 2. And again here, I multiply half times 1 plus root 3 times a half. I get a half plus root 3 over 2. Again, minus root 3 over 2 times 1 plus 1 times a half. I get minus root 3 over 2 plus a half. And then lastly, minus root 3 over 2 times 1 plus 1 times a half. That's minus root 3 over 2 plus a half. So this is what I now have. Now here, this can be simplified to, I have the half here, and at the top we can have 1 plus root 3 all over 2, 1 plus root 3 all over 2, and here we can have it as 1 minus root 3 all over 2, and 1 minus root 3 all over 2. And now factoring out a half, then the half multiplies the half that's already outside to give us a quarter. So we are left inside with 1 plus root 3, 1 plus root 3, 1 minus root 3, and 1 minus root 3. So now we have the matrix N simplified. So that's how we do it. We can now scroll down to part D. So on part D, they say, find the equations of the invariant lines through the origin of the transformation in the xy plane represented by Mn. So now we have the matrix Mn, and from part C we got Mn to be the matrix 1, 1, a half, and a half here. Now the invariant lines through the origin are lines of the form y is equal to mx. And if x is equal to k, then y is equal to k. So therefore, the general point for any point on any of those lines will be the point k and mk. That is, if we substitute k for x. So that's the general point for any point on these lines. So it means that if we are going to transform through this matrix Mn, which is 1, 1, a half, then this is going to give us an image xy. So this is what we're going to work on. So here I'll multiply row by column, top row and column. We get 1 times k plus 1 times mk. We get k plus mk. And half times k plus half times mk, we get a half k plus a half mk. So this gives us an image xy. So we're saying here x is equal to k plus mk and y is equal to half k plus half mk. Now, since the equation of the lines is y is equal to mx, for y I'll have a half k plus half mk, and that's equal to m of x, which we got to be k plus mk. So I'll simplify, but I'm sure you can see that k appears on all the terms. So I'll divide it out. I'll divide it through so that it gets eliminated. So we now have a half plus half m is equal to m plus m squared. Now I can multiply all the sides by 2, but let me scroll down a bit. So I'll be having this coming out as 1 plus m is equal to 2m plus 2m squared. This gives us an equation 2m squared plus m minus 1 equal to 0. And I can factorize this. So I'll have 2m here and m here, and I will have minus 1 here and plus 1 here. So I've thus factorized it. So we get the values of m as a half and m as minus 1. So if we are going to substitute these values into the equation y is equal to mx, then it means that we'll be having the equations for our solutions. Y is equal to half of x and y is equal to minus 1 of x, which is minus x. So these two become the two solutions. And that's it for this question. Question number 5. The curve C has polar equation r is equal to a cot a third pi minus theta, where a is a positive constant and theta ranges between 0 and a sixth pi. It is given that the greatest distance of a point on C from the pole is 2 root 3. So on A they say, sketch C and show that A is equal to 2. So when sketching the polar curve C, we can make a little table of values like this one. So we can have values that are ranging between 0 and a sixth pi at regular intervals. So these are values that are gonna help me to plot out or map out the polar curve C. Now substituting into the equation, when theta has a value of 0, you find that r will be having a value of 0.58a. And when theta has a value of pi over 24, r will have a value of 0.77a. When theta has a value of pi over 12, r will have a value of a. And when theta is a value of pi over 8, r will have a value of 1.3a. And lastly, when theta is a value of pi over 6, then r will have a value of 1.73a. Now with this table of values, I can consider a plane where I can plot out the graph. So I'm now plotting out my points. R values, when theta is equal to 0, r is 0.577, so I can put the point somewhere around here. And when theta is pi over 24, we have 0.77a, which is just below a, so maybe around here. And when theta has a value of pi over 12, then we have a as the value, so here. When theta has a value of pi over 8, that's 1.30a, so just outside somewhere here. And lastly, when theta has a value of pi over 6, then that's 1.73, which is maybe somewhere around here. So I think you can see how the graph is coming out to be like. So here we have the initial line where theta is equal to 0. And from the initial line, the graph seems to be going this way. So this is the graph. And the pole is round about here. Now the question also says it is given that the greatest distance of a point on C from the pole is 2 root 3. So the greatest distance should be the distance up to this point. So if we consider the equation r is equal to a cot of a third pi minus theta, then r will have a value of 2 root 3. That's the greatest distance, and that's a cot a third pi minus theta. So the theta value we said is a sixth pi. So we can solve for a here. So what I can do is I can say 2 root 3 is equal to cot is 1 over 10. So that's like a over, and a third pi minus a sixth pi is a sixth pi. So this therefore means that a is equal to 2 root 3 times 10 of a sixth pi. And we know that tan of a sixth pi is 1 over root 3. So it's like 2 root 3 times 1 over root 3. And this means that the root 3 and the root 3 will cancel out. And we have our answer as 2. So that's how we can prove. Let's go on to part B. So on part B, the question goes, find the exact value of the area of the region bounded by C, the initial line, and the half line. Theta is equal to a sixth pi. So in our case here, the area that we're looking for is this area here, bounded by the curve, the initial line, and the half line. Theta is equal to a sixth pi. Now, in order for us to find the area bounded by the graph, what we're going to do is use this formula here. So since in our case, we got a to be 2, the equation of the curve is 2 cot a third pi minus theta. Now, applying this into the formula for area, we say area is equal to, factoring out the 2, that will be 2 times the integral from 0 up to a sixth pi. Those are the limits of cot squared of a third pi minus theta. And that's with respect to theta. Now we can apply the identity cot squared plus 1 is identical to cosec squared theta. So that means that applying that identity, we'll be having 2 of the integral from 0 up to a sixth pi as the limits of cosec squared of a third pi minus theta minus 1 with respect to theta. Now we know that if we integrate cosec squared of a third pi minus theta, we are going to get cot as the integral. So that's cot of a third pi minus theta, and integrating 1 we get theta, and we'll be having the limits here, that's 0 up to a sixth pi. Now I can substitute a sixth pi. Let me scroll down first. So I can substitute a sixth pi into this. So I'll be having here 2, and substituting a sixth pi, we know that a third pi minus a sixth pi gives us a sixth pi, and cot of a sixth pi is as good as 1 over 10 of a sixth pi, and that's substituting a sixth pi on theta, that's minus a sixth of pi, and substituting 0 here, we'll be having minus of 1 over 10 of a third pi, and that's minus zeros. So this is what we now have. So we can simplify this a little bit more. Okay, 10 of a sixth pi is like 1 over root 3. So 1 over root 3 is like root 3. So this thing gives us root 3, and multiplying it by the 2 that's outside. So we have root 3 here, and that's minus a sixth of pi, and that's minus 10 of a third pi is root 3. So that's minus 1 over root 3. So that's as good as 2 root 3 minus a third pi, and that's minus 2 over root 3. Now, simplifying this by rationalizing the denominator, it's like we have 2 root 3 minus a third pi, and if we multiply this by root 3 over root 3, then it becomes 2 root 3 over 3, and this is going to give us an answer of, if we say 2 root 3 minus 2 root 3 over 3, we know that's 4 over 3, so we'll be having 4 root 3 over 3, and that's minus a third pi. So this here becomes the final answer. Let's scroll down to part C. So on part C, the question goes, show that C has Cartesian equation 2 bracket x plus y root 3 equal to bracket x root 3 minus y multiplying root of x squared plus y squared. Now here, I'm going to write down the polar equation of the curve C. So that's r is equal to a cot theta. We got a to be 2, so that's 2 cot of a third pi minus theta. Now, what we're going to do here is I'm going to write it as r is equal to 2, and we know that the trig function cot can also be written as cos over sine. So that's cos a third pi minus theta over sine of a third pi minus theta. Now I can multiply both sides by sine of a third pi minus theta. So this 2 will cancel. And on the left side we'll be having r sine of a third pi minus theta is equal to 2 cos of a third pi minus theta. Alright, now I'm going to use the addition formula for these. Starting on the left side, it means we'll be having r sine of a third pi cos theta minus r sine theta cos a third pi. And that should be equal to 2 cos of a third pi cos theta. And that's supposed to be plus 2 sine of a third pi sine theta. So we can simplify this. We know that sine of a third pi is root 3 over 2. So that's like root 3 over 2 here, r cos theta. And that's minus. We know that cos of a third pi, that's like cos 60, which is a half. So we'll be having here half r sine theta. On the right side, that's 2 cos a third pi cos theta. That can be written as 2 of cos of a third pi is half. So we have a half cos theta here. And that's plus 2 sine of a third pi, which is 2 of root 3 over 2 sine theta. So here we can cancel out this and also multiply both sides by 2. So by 2, so they will cancel. Then by 2, then this will cancel. So this one by 2 and this one by 2. So we'll now be having on the left side root 3 r cos theta minus r sine theta is equal to 2 cos theta plus 2 root 3 sine theta. So this is what we now have. Now for cos theta, we can use this important result to say cos theta is x over r. So it's like we have root 3 r is x over r. And that's minus r of sine theta should be y over r. And here we said cos theta is x over r. And here sine theta is y over r. Alright. So we know that the r's will again cancel on this side. So on the left side we'll be having x root 3 minus y is equal to, and on the right side we'll be having at the top that's 2x over r, and that's plus 2y root 3, and it's all over r. So we can multiply both sides by r. So by r and this side by r. So the r's on the left side will cancel out, and we will have the left side as r of x root 3 minus y, and on the right side we'll be having 2x plus 2y root 3. Now using the special results, on the left side we can have r as the square root of x squared plus y squared, and that's multiplying the bracket x root 3 minus y, and that should be equal to, here I can factor out 2, so that's 2 of x plus y root 3. Alright, so what we now have is actually the answer, and we can write it down as required by the question in the order that the question gives. So it's 2 of x plus y root 3 is equal to x root 3 minus y bracket and the root x squared plus y squared. And that's the answer right here. Question number 6. Let t be a positive constant. The line L1 passes through the point with position vector ti plus j and is parallel to the vector minus 2i minus j. The line L2 passes through the point with position vector j plus tk and is parallel to the vector minus 2j plus k. It is given that the shortest distance between the lines L1 and L2 is root 21. So on A, find the value of t. So right here we've got two lines, and I would want to write the equations of the lines in column vector form. Let's start with the line L1. The line L1 has a position vector ti plus j. In column vector form, that's t1 0, and that's plus the parameter lambda and is parallel to the vector, so the direction vector is minus 2i minus j. That's minus 2 minus 1 0. So that's the line L1. And the line L2, for the line L2, they say the position vector of a point on the line is j plus tk, so that's 0 1 t. And I'll use mu here. The direction vector, they say it is parallel to the vector minus 2j plus k, which is 0 minus 2 1. So I now have the two equations in column vector form. Now, in order for us to find the shortest distance between two lines, we can use this formula. So applying this formula, I'll need first to find my A1 minus A2. So in this case, that'll be T10 minus 01T. So this should give us T minus 0, that's T, 1 minus 1, that's 0, and 0 minus T is minus T. So we now have A1 minus A2. And I'll also need to find the cross product B1 by B2. So that's the cross product of the direction vectors. So for the direction vectors, I have minus 2 minus 1 0 multiplying 0 minus 2 1. Alright, so here for the cross product, I'll close out this 2. So I'll have minus 1 minus 2 0 and 1, and that's I. Then I say minus and I close out these two middle ones. So I'm left with minus 2 0 0 1, and that's going to be J. And then I'll close out the last two. So I'll be having plus, and that's going to be minus 2 0 minus 1 minus 2. And that's going to be K. So that's how we do the cross product. Let's simplify this. Here I'll have minus 1 times 1 minus 0 times minus 2. So this is going to give us minus I. And here minus 2 times 1 minus 0 times 0. And with the minus outside, we get plus 2j. And then lastly, we will have minus 2 times minus 2 minus minus 1 times 0. And that's going to give us 4k. So this is now what we have. This can also be written in column vector form as minus 1 2 4. So like this. So from the formula, I will also need the modulus of the cross product B1 cross B2. So that's simply going to be minus 1 squared plus 2 squared plus 4 squared. And this is going to give us 1 plus 4 plus 16, which is 21. So that's root of 21. Now, applying the formula, we are saying, according to the question, they say the shortest distance between the lines L1 and L2 is root 21. So we are saying root 21 is equal to, and we have A1 minus A2, which we got to be T0 minus T dot product with B1 by B2, which is minus 1 to 4. And it's O over modulus of B1 cross B2, which is root 21. So it's O under modulus. So with this here, if we multiply both sides by root 21 will multiply with this root 21, and we are going to get 21. And on the right, if we do the dot product here, we get T times minus T, T times minus 1, which is minus T, plus 0 times 2, which is 0, plus minus T times 4, which is minus 4T, and minus T minus 4T is minus 5T. And since we are under modulus, we'll only have 5T here. Then we can divide both sides by 5. So therefore, T will come out as 21 divided by 5, which is 21 over 5, which as a decimal is 4.2. So that's the value of T right here. Let's scroll down to part B. So on part B, they say the plane pi1 contains L1 and is parallel to L2. Write down the equation of pi1, giving your answer in the form R is equal to A plus lambda B plus mu C. Now, what we're going to need here for this plane is a point on the plane which is A. So it's going to be in the form R is equal to A. And what can we have as A? A is the point on the plane which can be a point on L1, and the point on L1 is the point T10, and we got T to be 4.2, so it'll be 4.210. So that can be the A. That represents a point on the plane. So it has to be a point on the line since the plane contains the line L1. And that's plus lambda B. So B is any direction vector that is parallel to the plane or that is right on the plane. So we can take the direction vector of the line L1 since it's already contained in the plane. So that's minus 2, minus 1, 0. So minus 2, minus 1, 0. And that's plus mu C. C is also direction vector contained in the plane or parallel to the plane. So we're going to take the direction vector of L2 for that, which is in this case 0, minus 2, 1. So that's 0, minus 2, 1. So this here is the equation of the plane pi1. We can scroll down to part C. On part C, the plane pi2 has Cartesian equation 5x minus 6y plus 7z equal to 0. So find the acute angle between L2 and pi2. So let's have the equation of the line L2. Now the line L2 is this line R is equal to 0, 1t plus mu 0 minus 2, 1. So let's just write down the equation. That will be R is equal to, and that's 0, 1t, 0, 1, and in place of t, we're putting 4.2. That's the value of t that we got. And that's plus mu of 0 minus 2, 1. And how about the plane pi2? For the plane pi2, in column vector form, that's R dot 5 minus 6, 7 equal to 0. So we now have the two equations of the line and one of the plane in column form. Now first, I'll need to find the angle between the line L2 and the normal to the plane pi2. So I'll get that by cos of theta is equal to the direction of L2, that's 0 minus 2, 1, dot, and the normal to plane 2 direction, that's 5 minus 6, 7, and it's over the square root of 0 squared plus minus 2 squared plus 1 squared, and that's times the square root of 5 squared plus minus 6 squared plus 7 squared. So for the dot product at the top there, that's 0 times 5, which is 0, plus minus 2 times minus 6, that's 12, plus 1 times 7, which is 7. And that's over. Here we'll be having the square root of 0 squared plus minus 2 squared plus 1 squared, that's root 5. And that's times 5 squared plus minus 6 squared plus 7 squared, that's 25 plus 36 plus 49, that gives us 110. So that's all cos theta. So we are saying cos theta is equal to 12 plus 7, that's 19, over root 5 times root 10, that's root of 550. So to get theta, we say arc cos of 19 over root of 550. And using the calculator, we're saying shift cos of 19 over root of 550. And that gives us the angle 35.9. So that's 35.9 degrees. Now remember, the angle theta here is the angle between the line L2 and the normal to the plane. Now to get the angle between L2, so now the angle between L2 and pi2, we will say 90 minus 35.9 degrees, and we will get the answer as 54.1 degrees. So that is the answer right here. Let's go on to part D. Part D goes, find the acute angle between pi1 and pi2. Alright, so again, we're going to need the equations to the planes. Let's start with the plane pi1. Now, the plane pi1, we got it as this one here. That's the equation of the plane pi1. So I'll just take this and I'll just paste it here. So this is pi1. Now I'll need to write this equation of the plane in the form r dot n is equal to d. So what I'll do is I will do cross product. So I'll have the directions minus 2 minus 1 0, cross multiplying 0 minus 2 1, and this is gonna give me, closing out the top numbers, we have minus 1 minus 2 0 1 I, and that's minus. Here closing out the middle ones, we have minus 2 0 0 1, and that's j, and closing out the bottom numbers, that's plus, and that's minus 2 0 minus 1 minus 2, and that's k, right? So here we'll be having minus 1 times 1 minus 0 times minus 2, that's minus I, and here we'll be having minus 2 times 1 minus 0 times 0, so that gives us plus 2j, and here the last one is minus 2 times minus 2, that's 4, and minus 1 times 0 is 0, so that's plus 4k. Now what we have here is the normal to the plane pi1. So that's all we need in order for us to calculate the angle between the two planes, right? So this is the normal to the plane. So now that we have the normal to the plane pi1, the plane pi2 is the one that we got right up here. That's 5x minus 6y plus 7z. So I'll just paste it here. So this here is the plane pi2. So to get the angle between the two planes, I will say cos of theta is equal to the dot product of the normals. That's for pi1, that's minus 1, 2, 4, and that's dot. And for this one, I have 5, minus 6, and 7, and that's going to be over, and that's the square root of minus 1 squared, so minus 1 squared, plus 2 squared, plus 4 squared, and that's times the square root of 5 squared, plus minus 6 squared, plus 7 squared. So this is going to give us, at the top, we'll be having the dot product minus 5 plus 2 times minus 6, that's minus 12. So that's minus 12. And 4 times 7 is 28. And it's all over. At the bottom, we'll be having square root of 1 squared plus 2 squared plus 4 squared, which happens to be square root of 21. And that's times the square root of, here we have 5 squared times 6 squared times 7 squared, which gives us 110. So this simplifies to minus 5 minus 21 plus 28. That gives us 11. And that's over 21 times 110. That's 2,310. So therefore, theta is arc cos of that 11 over root of 2,310. And what does that give us? Let's use the calculator. Shift cos of 11 over square root of 2,310. And this gives us the angle 76.8 to 1 decimal place. And that's the answer right there to part D. Question number 7. The curve C has the equation y is equal to x squared plus x plus 9 all over x plus 1. So on A, find the equations of the asymptotes of C. Alright, so here we're going to start with the vertical asymptote. And for the vertical asymptote, we find it when the denominator x plus 1 is equal to 0. So the equation of the asymptote here is x is equal to minus 1. So that's the vertical asymptote. And then for the oblique asymptote, we're saying we are going to divide, since we have y is equal to x squared plus x plus 9, and it's all over x plus 1. Then if we divide x plus 1 into x squared plus x plus 9 and we get the quotient, that'll help us get the equation of the oblique asymptote. So you can do long division, or even by inspection, you can notice that we can express or factorize x squared plus x by factoring x out. So that's x bracket x plus 1 and it's plus 9. And that's all over x plus 1. And this is the same as x of x plus 1, all divided by x plus 1. And that's plus 9. And that's over x plus 1. Alright, so you can notice that we can cancel out the x plus 1s here. And we're left with x plus 9 over x plus 1. So that's y is equal to x plus 9 over x plus 1. So the quotient here is x, and with the quotient we can come out with the equation of the oblique asymptote. So the equation of the oblique asymptote is y is equal to x. So we now have the two equations, one for the vertical asymptote and the other one for the oblique asymptote. Let's go on to part B. On part B, it goes, find the coordinates of the stationary points on C. Now I'm going to take the equation of the curve C. So here it is. So this is the equation of C. And I'm going to find dy by dx. Okay. So I'm going to use the quotient rule, where I'll take the numerator to be u and the denominator to be v. So using the quotient rule, I have my u being equal to x squared plus x plus 9, and therefore the derivative of u is 2x plus 1. And then I have v to be x plus 1, so the derivative is 1. So I'll then say, therefore dy by dx is equal to vu prime, which is x plus 1 multiplying 2x plus 1, and that's minus uv prime, which is x squared plus x plus 9 multiplying 1, and it's all over v squared, which is x plus 1 squared. So we can simplify here. Simplifying the numerator, the two brackets here gives us 2x squared plus 3x plus 1, and that's minus x squared minus x minus 9, and it's all over x plus 1 squared. So that's 2x squared minus x squared is x squared, and 3x minus x, that's 2x, and 1 minus 9 is minus 8, and that's all over the denominator, x plus 1 squared. So this is the expression for dy by dx. Now, since it's a stationary point, we know that at stationary point, dy by dx is equal to 0. So therefore, we are going to equate this expression to 0. And if we do, we will multiply both sides by x squared plus x plus 1 squared. And we will eventually get x squared plus 2x minus 8 being equal to 0. Now, by factorization, we have x here and we have x here. We should have 4 and 2, and this should be plus and this should be minus. So therefore, the values of x are minus 4 and 2. Now, we also need to know what the corresponding y values are. It means that we will need to substitute minus 4 into the equation here of y. And if we do, we'll eventually get the coordinates of stationary points to be, when x is equal to minus 4, y should come out as minus 7. So that's minus 4 and minus 7. And if x is equal to 2, substituting into the equation here of y, we get the value of y to be 5. So that's 2, 5. So these two are the coordinates of the stationary points. Let's move on to part C. On part C, the question goes, sketch C stating the coordinates of any intersections with the axis. Alright, so what we're going to do here is to make a sketch. So I have my axis. So this here is y and x. And I'll start with the two asymptotes. So the first asymptote is x is equal to minus 1, and the other one is y is equal to x. So let's start with x is equal to minus 1. That's the first asymptote. So it intercepts at minus 1 here. And then we have the oblique asymptote right here. And now my graph will come out like this. I have to consider the fact that we've got two stationary points, and that's at -4 and -7 and 2, 5. So I know that my graph is gonna be coming out like this. So there's an intercept here on the y-axis, and to get the y-intercept, I'll take the equation and say for the y-intercept, x is equal to 0. And when x is equal to 0, y, substituting 0 here, we get y being 9/1, which is 9. So the coordinates here are 0, 9. We are going to plot out the other part of the graph, which has a maximum stationary point, and here it is. Alright, so now we have the graph, and we can scroll down to part D. So on part D, it goes, sketch the curve with the equation y is equal to mod x squared plus x plus 9 over x plus 1, and find the set of values of x for which 2 of mod x squared plus x plus 9 is greater than 13 mod x plus 1. Alright, so this is a modulus graph. So this means that I'm going to reflect the part of the graph that is below the x-axis above the x-axis. Alright, so if I am going to do that, it should come out like this. So the asymptote is reflected this way. So we managed to reflect the part that was below the x-axis above the x-axis. So this is what we now have. So now that we have the modulus graph, we also want to answer the part that goes, find the set of values of x for which 2 mod x squared plus x plus 9 is greater than 13 mod x plus 1. Okay, so how are we going to do that? If I take this equation and I divide both sides by 2 of mod x plus 1, then I see that I can cancel this and be left on the right side with 13 over 2. And on the left side, I can cancel out the 2's, and I'm left with x squared plus x plus 9, and it's over x plus 1, and it's all under modulus. So if you look at this modulus expression, that's the same as the one that we have for the curve. So here we're considering y is greater than 13 over 2, which means that I'm going to go on the graph and I'll draw the line y is equal to 13 over 2, which is 6.5. So it should be somewhere around about here. So this is the line y is equal to 13 over 2, which is as good as 6.5 as a decimal. So this is the line here. So we have two critical points in which one is here and the other one is right here. So I'm going to say for the intersection of this part of the curve and the line y is equal to 6.5, I'm going to solve x squared plus x plus 9 over x plus 1 being equal to 13 over 2. So if I cross multiply, then I'll get 2 of x squared plus x plus 9 is equal to 13 of x plus 1. So that's 2x squared plus 2x plus 18 is equal to 13x plus 13. So that's 2x squared, and that's minus 11x, and then that's plus 5 is equal to 0. So factorizing, we will get 2x here and x here, then minus 1 and minus 5 here. So that's all equal to 0, and therefore the values of x from this we get to be a half and 5. So this means that this is a half, and this is 5. Now we want values of x that satisfy this inequality here, where the graph of y, that's the modulus graph, is greater than or above that of 6.5. All right, so we will take values of x, that's for the solution. We'll take values of x that are less than a half. That is where, if you look at this value here, you can notice that for values that are less than a half, values of x that are less than a half, the graph of the modulus is always greater or above that of y is equal to 6.5. And we also have values of x that are greater than 5, where the graph of modulus is also above that of y is equal to 6.5. So that's x greater than 5. So this becomes our solution set. That's the answer right here.